Welcome to this video lecture. This is Mark Scythian, FAA licensed aerospace technician, airframe power plant and avionics certified. The date today is July 8, 2016. In this video lecture we are going to discuss bolt stretch and compressive force of an aluminum bolt. When a bolt is tightened, a certain amount of foot-pounds of torque is applied to the bolt as it is tightened. When tightening a bolt, the bolt threads and bolt receiver threads exert an interlocking fit which causes the bolt to elongate or stretch somewhat. This causes a compressive force by the bolt head to exert upon the surface that is fastened by the bolt as the bolt is tightened upon the surface. Using the Young's modulus E tensile pressure value for a given material, the actual compressive force exerted by the bolt head upon the surface can be calculated. The Young's modulus E tensile or compressive pressure in pounds per square inch represents the maximum pulling or pressing a given material can tolerate before it will yield or permanently deform preceding failure of the given material. Young's modulus E is equal to stress divided by strain, where stress is the force compressive or tensile divided by the cross-sectional area of the material in either metric or US units, which we'll cover in a second, but it's the tensile or compressive force divided by the cross-sectional area, which represents the stress, and the strain is the elongation or compression divided by the length of the material. So that's stress divided by strain mathematically illustrated. So assume that an aluminum bolt, which is 3 inches long, excluding the bolt head, has a shank diameter of 1/4 inch and is tightened upon a surface to be fastened at a certain torque setting. After the bolt is tightened to a certain foot-pounds torque setting using a torque wrench, a bolt stretch elongation to the 3-inch long shank of 0.001 inches takes place. How many pounds of compressive force is the bolt head exerting upon the fastened surface after the bolt is tightened if the Young's modulus E for aluminum is 10 million psi? So we go to the formula again. Young's modulus E is equal to the tensile or compressive force divided by the cross-sectional area as the stress divided by the strain, which is the elongation or compression divided by the effective length. So if we define the terms, E is the Young's modulus tensile pressure in pounds per square inch or pascals. That's US and metric values. Either or, you got to keep them consistent. Tension or compression force in pounds or newtons is the F. The A represents the cross-sectional area of the material in square inches or square meters. DL is the elongation or compression in inches or meters. L is the effective length of the material in inches or meters. So we start with a Young's modulus E for aluminum of 10 million psi. Cross-sectional area is just pi r squared, so we just take the diameter of 1/4 inch, 0.25 inches, divided by 2 to get the radius, square that times pi, and that turns out to be 0.049 square inches of cross-sectional area to the bolt. And then there is an elongation, when tightened, of the bolt shank of 0.001 inches, and then the effective length is the shank of the bolt excluding the head, which is measured at 3 inches. So L is equal to 3 inches. So all we had to do is algebraically calculate it out. We just plug in all the values we know, the Young's modulus E, we don't know the force, divide it by the cross-sectional area, the elongation, and the length. Then all we do is we can solve for the denominator. And then after that, since this value here would be equal to, when you multiply the 10 million times the denominator, you get the numerator, right? So right there you can just multiply the 10 million times the denominator and then equal it to the fraction of f over 0.049. Then when you do that, the 10 million times this value becomes 3330, and then you just solve for f. So when you do that, you get this final computation. So 163.17 pounds of compressive force is the calculation. So the given aluminum bolt's head, is exerting 163.17 pounds of compressive force when tightened to the given foot-pounds setting that causes a bolt stretch of 0.001 inches. A bolt stretch to the shank, that is, 3 inches of shank. Another example is using a bolt stretch gauge to determine how much bolt torque will be required to cause a bolt's head to exert a certain amount of desired force onto a surface. The compressive force for, let's say, a piston engine cylinder head at each bolt receiver, let's say, requires 180 pounds of force upon a certain surface area. The technician can take the given bolt, install it into a bolt stretch gauge, and use a torque wrench to tighten it until the desired bolt stretch takes place, measured by the bolt stretch gauge itself. The desired bolt stretch is first computed by using the Young's modulus formula. The compressive force needed, F, is taken by solving for the bolt stretch DL required based on the Young's modulus of the given material E, cross-sectional area of the bolt A, and length of the bolt L, excluding the bolt head. When the bolt is screwed into the bolt stretch gauge and tightened with a torque wrench, when the desired bolt stretch is reached, measured by the bolt stretch gauge, as the bolt is tightened into the bolt stretch gauge, then the foot-pounds torque at the torque wrench is measured. This will then be the required foot-pounds torque that the bolt must be tightened at in order to allow the bolt head to exert the 180 pounds of desired compressive force upon the given surface, in this case the piston and engine cylinder head, at that point where the bolt is to be installed. So any one of those variables can be solved on the Young's modulus formula, tensile pressure, once you get the E of the material you're working with. And this is very valuable if you want to figure out the bolt stretch or how many pounds of actual force the bolt head is exerting on a surface when it's tightened upon it. Thank you for watching this video and have a great day.